Okay, we were discussing about the various filtering techniques which are used to eliminate this noise or interference from the biomedical signals, especially in the ECG signal. So we have discussed some time domain filters till now. So how you can design filters the time domain to remove the power line frequency or the baseline wanders, the Hanning filters. Okay, these filters based on the first derivative differences and so on that we have discussed. One more category of filters which is used normally to remove the noise from the signal is in the frequency domain. Okay, so in the frequency domain filter, the most common or the generally used filter is a Butterworth filter. Okay, such type of filters, they are described in the frequency domain in terms of the frequency response. Okay, so for a Butterworth filter, the frequency response of a filter is defined as, if you talk about analog filter, it is magnitude scale response is equal to 1 upon 1 plus omega by omega c to the power 2n. Okay, so it is described by two parameters. One is omega c, which is now the cutoff frequency. Another is this parameter n, which is called as order of this filter. Okay, so if you put omega is equal to omega c in this equation, or you say that for, you'll simply get 1 by 2 for all values of n. So whatever is the filter order at cutoff frequency, the magnitude scaled response will be 1 by 2. Okay, or the magnitude of this, the magnitude response of the filter will be 1 by root 2. Okay, so this filter, if you plot this response of this filter mod h omega square with respect to omega, so this filter has a response, it has a flat response in the pass band and a flat or monotonic response in the stop band. This is the response of a Butterworth filter. Okay, so this is the frequency, which is omega c, the cutoff frequency, so at which the magnitude scaled response is 1 by 2. Okay, so it has a monotonic response or a flat response in the pass band and in the stop band. This is the most desirable characteristics of Butterworth filter. So if you choose any omega c here and any value of n, and you plot this response, you will get a response like this. Okay, and for different values of this n, which is the order of this filter, the cutoff frequency of course remains n. If you change the order, what will be changing in this response is that for higher orders you will get a sharp transition from pass band to the stop band. So this is for suppose n is equal to maybe 4, so this may be for n is equal to 8. Okay, so the cutoff frequency will remain same. Okay, so as increase the order of the filter, you get more and more sharp responses in the frequency domain. Okay, but the complexity of the filter will basically increase if you increase the order of the filters. Okay, now how we use the Butterworth filter in, or how we design basically Butterworth filter for filtering of this noise. If you go into a little bit more detail, you might have studied in your circuit theory or network analysis subject also these filters. But anyhow, we have defined a Butterworth filter like this. Magnitude response. Okay, now how to design such a filter? If omega c and n, so omega c and n must be given to you, the cutoff frequency and the order of the filter. If they are specified to you, you can design this filter. Okay, and how you can design a digital Butterworth filter if the cutoff frequency and the order is given, that we'll discuss. This magnitude scale transfer function, you can write it as on the left side h of s into h of minus s is equal to 1 plus, it will become minus s square upon omega c square to the power n. Okay, now what I can do is I first write this equation as 1 upon 1 plus omega square upon omega c square to the power n. I can write like this. Okay, now since it is the magnitude response, it will be the product of the two transfer functions h of s and h of minus s. That will give you h of mod h of omega square. Okay, so in the Laplace domain now, this is the transfer function or the product of the two transfer functions in fact, and in C, if you put s is equal to j omega, you will get again the frequency response. So this equation or this will turn to be this. If you put s is equal to j omega, your Laplace converts to Fourier, and you will get again 1 upon 1 plus. So since this is minus s square here and s is j omega, it will become j square omega square, and j square is minus 1, so that minus and this minus will become plus. You will get again omega square upon omega c square to the power n. Okay, so in terms of Laplace transform, you can write this equation. Okay, now it has only poles. You can see there are no zeros. Okay, if you want to find the poles of this filter, you can equate the denominator to 0. So you have to equate 1 plus minus s square upon omega c square to the power n. It has to be equated to 0. Okay, that will give the poles of the filter. Or you can say minus s square upon omega c square to the power n is equal to minus 1. Okay, or you can write it as minus s square upon omega c square is equal to minus 1 to the power 1 by n, and minus 1 to the power 1 by n, you can write it as, so now the nth root, it is e to the power j 2k plus 1 pi by n. Okay, if k is equal to your 0 up to n. Okay, so if you this minus 1 to the power n minus 1 to the power 1 by n, so that I have written like this. Okay, so if you raise to the power n, from this equation what you will get, I write it here, you will get minus s square is equal to omega c square into e raised to power j 2k plus 1 to pi by, in some books it is also written 2k minus 1. Okay, so s square will be equal to, minus will go here on the right side, and in place of minus 1 you can write it as e to the power j pi, isn't it? Because e raised to power j pi is minus 1. Okay, so multiplied with e to the power j 2k plus 1 pi by n. So finally your s, which is equal to omega c into e raised to power j pi by 2 multiplied with e raised to power j 2k plus 1 pi by 2n. So you can write as omega c e to the power j pi, you can take as common. So what you will get inside is 1 by 2 plus 2k plus 1 upon 2n. So you can write it as k for different values of k. So this gives you the location of the poles of the Butterworth filter in the S-plane. Okay. So it started from this Laplace transfer function, equated denominator equal to 0, so minus 1 to the power 1 by n. Okay. So nth root of minus 1, that is this. If you again raise it to the power n, you will get again minus 1. Okay. This n and this n will get cancelled. So it's for j2 pi plus k plus 1 pi, it will become again minus 1, right? So finally we get this equation. So these are the poles of this Butterworth filter in the S-plane. Now you will see that these poles will be placed, if you just look how these poles, location x k is equal to, it is omega c e to the power j pi into 1 by 2 plus 2k plus 1 upon 2n, location of poles. Okay. Now since it is a complex number, if we take magnitude of this, it is nothing but omega c. Okay, because exponential term, its magnitude will become 1. It means these poles, they are basically lying on a circle of radius omega c in the S-plane. Okay, so if n is given to you, you can simply plot these poles. Okay, suppose if your n is equal to 4, the Butterworth filter order is 4. So what is the location of poles? So you put k is equal to 1 here, you will get omega c into e raised to power j pi 1 by 2 plus 1 by 8. Okay, so you get e raised to power j pi 8, 4 plus 1, 5 pi by 8. Okay, so cos 5 pi by 8 plus sin pi by 8. So pi by 8 is it will lie somehow around here. This is pi by 8. So one pole will be here. Okay, then you put k is equal to 2, you will get again on the circle of radius omega c e raised to power j pi 1 by 2 plus k is 1 now, initially it was 0. So if k is 1, you will get 3 by 8. So you will get omega c e to the power j, it will become 8, 4 plus 7 pi by 8. Okay, so 7 pi by 8 is here. So you will get one pole here. And if you see the spacing between these two poles, it is pi by 4. It is pi by n. Now since the poles will always occur in the complex poles will always occur in the conjugate pairs. So corresponding to this, you will get its conjugate here, one more pole. And similarly, you will get one conjugate pole here. Okay. So the left half poles, the poles in the left half plane, they will basically correspond to h of s. Okay. Similarly, you will have the right half poles here now. So they will correspond to a transfer function h of minus s. Okay. Now see how you design this filter. Now once you have the idea about the location of the poles in the S-plane from this equation, you can find the transfer function of this filter h of s by combining all these poles. That is, you can say s minus s1 into s minus s2 into s minus s. Suppose you have n poles, so k poles, s minus s k, along with some constant g, which may be specified, or you can just use it to normalize the gain equal to unity at DC frequency. Okay, so once you have now this analog transfer function, then using the bilinear transformation that we already discussed in the IR filter design, where s is placed is 2 by t 1 minus z inverse 1 plus z inverse. So if you replace s with this using the bilinear transformation, your h of s converts to h of z. Okay, now you have finally a transfer function in the form of this. You have summation of b naught plus b1 z inverse plus b2 z for minus 2 and so on. 1 plus summation of it was ak, so we will have now a naught or a1 z inverse plus a2 z to the power minus 2 and so on. Okay, so from this you can find the filter coefficients b0, b1, b2, a1, a2. Okay, so you'll get a IR filter basically. Okay, and then you have different structures for implementing this, that you know, direct form 1 or direct form 2 or cascade or parallel structure. So you can implement this filter. Okay, so how we design now this filter, we will just see what are the various steps. So what you have to do is you have to specify the frequency and the order. Specify the cutoff frequency, omega c, and order of the filter. So if you want to design a digital filter, it must be omega c. Or if omega c is not given, it may be in the frequency in hertz c, then you have fs is given to you and n. Okay, so let us suppose you want to design a Butterworth low pass filter having a cutoff frequency of 40 Hz with a sampling frequency of 200 Hz. The filter order is 4. Okay, you have to design this digital filter for this digital Butterworth filter. Okay, so how you will do? So first you have to compute this. If omega c is directly given to you in the form of between 0 and 2 pi, then it is okay. But if it is given in the form of frequency in hertz like this, you have to compute omega c first. So omega c will be equal to 2 pi fc by fs. So you'll get the 2 pi into fc, that is 40 upon 200. You'll get 0.4 pi. Okay, so once omega c is and n is specified, then you have to rewrap, or you have to convert this digital frequency into the analog frequency using the frequency mapping that we have in the bilinear transformation. So in the bilinear transformation, you replace s with this 2 by t 1 minus z inverse 1 plus z inverse, and accordingly your frequency mapping is like this. It is 2 by t tan of omega by 2. This is a nonlinear mapping. Okay, so you've seen that how this frequency, how this analog frequency is converted into a digital frequency using bilinear transformation. So it is a nonlinear mapping basically. Okay, it means if omega is somehow, if your omega is here, if this is omega c, suppose like I'm getting at 0.4 pi, so you have to map this frequency to the corresponding analog frequency using this relation. So this frequency in the digital will become omega c is equal to this in the analog. Okay, so you have to compute omega c now. From this omega c, you have to find analog frequency using this relation 2 by t tan of omega by 2. Now once you get this omega c, then you have to find the location of poles of the filter in the S plane. Okay, so we already have a relation for that. The location of poles is given by omega c e to the power j pi 1 by 2 plus 2k plus 1 by 2n. So n is given to you, omega c now you have computed from this relation from part 2. So the poles will now lie on this circle of radius omega c in the S plane. Okay, so from this you can compute the poles. Once you compute the poles, so by combining all the left half plane poles, you have to compute a transfer function h of s, which is used in a log filter. Okay, so you have s minus s1, s minus s2. So in this case, for n is equal to 4, you have 4 poles in the left half plane, you have s minus s3 into s minus s4 multiplied with some constant again. Okay, so these poles are on a circle of radius omega c. So omega c you can compute from this. Okay, what you'll get. So like say for n is equal to 4, we have seen that okay, one pole was here, it was 5 pi by 8, another pole was here, it was 7 pi by 8, and then their conjugates. Okay, so 4 poles. So what is the location of this? If you turn into the face, it will be cos of 5 pi by 8 minus j sine of 5 pi by 8. This is what is your S1. Similarly, you can find S2, S3 and S4. So once you get these input into this equation, you can get a algebraic equation of h of s. It will be now, so if you multiply these two, this and its conjugate, become one function. So it will be, it's called order 4 filter. Okay, s to the power 4. And after this, then your last step is you have to convert this analog filter and digital filter using bilinear transformation, that is by replacing s with 2 by t 1 minus z inverse upon 1 plus z inverse. So using this, your h of s is converted to h of z. And once you have this h of z, so you can compare this with the general expression of a IR filter. You can find the numerator coefficients b0, b1, b2, and denominator coefficients a1, a2, a3, and so on. So this is how your filter will be designed. Okay, so these are the steps which are involved in the design of Butterworth digital filter. Okay, so similarly you can use it for the high pass filter. Then there are more filters like a Chebyshev filter, elliptical filters. So they are very much similar to this Butterworth filter. So you design a filter in the analog domain, and then using the bilinear transformation, you convert this filter into a digital filter. Okay, so normally for like, if you see for these biomedical signals, like for baseline wonder, we have used a filter in the last time. So if you use a Butterworth low pass filter to eliminate this baseline frequency from this, okay, so you have to pass only the you have to pass only high frequencies, you have to reject the low frequencies. So you said that okay, the filters must have a response like this. Okay, so the cutoff frequency now it is 2.7 hertz. So normally we use a band pass filter. When you process the ACG signal, we use a band pass filter between a frequency of 0.7 to around 100 hertz. Okay, because this is the major bandwidth of ACG signal. Okay, so beyond 100 hertz you have high frequency noise. So below 0.7 hertz you have low frequency noise like baseline wonder. So these noises will be basically netted if you use this pass band. Okay, so this is how various filtering techniques they are used to, you can say, process these biomedical signals.